Good morning, everyone. Good morning. Let me get here where the lights are. Welcome, guys. What a wonderful room today. Welcome, everyone at home watching us, everyone on YouTube, also reviewing the wonderful things that we are going to do today. And it's such a pleasure to be here with you among students. I remember when I was a student, I loved being where you are, and I look at all of you that are getting a diploma today, and I have this feeling that I'm getting young again, which is unfortunately doesn't get truth anymore, but I totally relate to the happiness and to the positive energies that you have today. Welcome to the 27th Symposium of the Federation for European Education in Gemology, a federation with associations and educational organizations all across Europe. And today we celebrate the 30th anniversary of FEEG, which is about my age, and it's a very good plastic surgeon. And it's wonderful to have, as a celebration, a fantastic lineup of very high-level speakers. You will get a treat of gourmet knowledge and science and education from the wonderful speakers that we will have for you today. So it's really a pleasure to be here. It is an honor to be the master of ceremonies of this symposium, of this educational event. And I call to the stage the current chairman of the Federation of Education, European Education in Gemology, and director of ENG, the Italian Gemological Institute, Dr. Ilaria Adamo.
Thank you so much, Rui, for your introduction. It's a great pleasure for me to welcome all of you to the 27th Symposium of the Federation for European Education in Gemology, which marks also a significant milestone in our history, the 30th anniversary. This event is organized by the Italian Gemological Institute in partnership with Vicenza Oro. And I would like to sincerely thank both of them for all the support in organizing this event. I would like to thank all the speakers for coming. I would like to thank the delegates, Rui, of course, for accepting the very important role of the Master of the Ceremonies, of course, all the graduates and all of you for being here today. And now, some words about our federation. Our federation was founded in August 1996, with the first examination in October and the first symposium in Paris in 1999. And today we are celebrating 30 years from the beginning of our federation. We are very proud of this achievement. These years represent a journey shaped by people that believed in this project and worked to build a strong organization. And today is an opportunity to honor the people that founded the Federation and the people that continue to contribute every day with dedication to its growth. The Federation offers first-class education in gemology in 12 teaching centers in 8 European countries, from Austria, Belgium, England, France, Germany, Italy, the Netherlands, and Spain. Every year we celebrate the students that achieve the European certification with hard work and dedication. And awarding the diplomas is the most important part of our symposium, since our graduates represent the future of gemology. Now, I would like to show you some picture about the history of the federation. Okay, this is a picture showing the first three presidents of FEEG, Dr. Bank, Dr. Hen, and Dr. Nogues, during the 50th symposium of FEEG in January 2003. This is a more recent picture from the 20th anniversary in Ida Oberstein, Germany, in November 2016, the delegates and the graduates. And here we were always in Vicenza in September 2019, during the 21 symposium in Vicenza. And here you can see a picture of the graduates and delegates from the 2050 anniversary of our federation in Paris in September 2022. And today we award the diplomas to 87 new European gemologists, which bring us to a total of 1,764 since the beginning of our federation in 1996. And our goal is always promoting excellence in the gemological training. May the 30th anniversary not be seen only as a point of arrival, but rather as a new beginning, inspiring us to continue building the federation together. I wish you all a productive and inspiring day, and I hope you will enjoy today's topic as much as I do. Thank you so much. Grazie mille a tutti.
Grazie, Lara. Grazie mille. What a wonderful presentation to show that education is the key. And as the black belt in judo, it's not the end, it's the beginning. Getting a diploma, it's the beginning of a wonderful thing ahead of us. Mi dispiace allora perché io vai a questo momento parlare mio miglior italiano con un fortissimo...
I'm so sorry, I will be speaking the best of my Italian with a very strong Neapolitan accent. I would like to ask the president of the Italian Gemological Institute, Raffaello Magno, to join me on stage.
Bravissimo.
Good, welcome to you all. I will be very briefly addressing you to then leave enough space to the well-known speakers. It is very interesting indeed that the Gotha of European Gemology is attending this meeting, which makes us feel very proud of this meeting, especially we, the IGI, organizing this meeting. So, and IGI, as a founding member of FEG, is proud of all the events that have happened. IGI is very proud of it, and all of the members who have been following IGI's activities in the course of time are very proud of the results we've obtained. So at this point, let me apologize for not speaking English. I hope you will be able to follow me. I'd like to thank all those in attendance as well as all the speakers. And I'd like to leave the floor now to people who know more than I do in the field of gemology. Thank you very much indeed, Raffaele.
It is what everybody was looking for and waiting for today. It is my honor to call upon the stage the very first speaker of this symposium. I call Damien Cody to the stage. This is his curriculum. I will start to read it. So, well, he is the current president of the International Cholera Gemstone Association. He's also chairman of the Opal National Collection. He's an expert on opals. I can tell you a few stories about Damien.
Better not.
Okay, better not. But I have to say this. Damien and his late brother Andrew, they were very keen in promoting education, in promoting the understanding of their gemstone of passion, that is opal. So it's a privilege for all of us to have here today on the stage Damien Cody. Thank you very much. I didn't read everything. I'm sorry.
He's left a lot out, thank goodness. Thank you to FEEG for having me here today. It's an absolute pleasure. It was a long way to come, but it's been most worthwhile. It's my first FEEG, and it's my first Vincenza Auto, and it's an incredible event that you're putting on, and I've been delighted with the Italian hospitality and the beautiful countryside here, so it won't be my last trip here, that's for sure. I'm going to be speaking about a topic I'm passionate about. I'm normally talking about industry events and talking about ruby, emerald, sapphire, but of course my real passion is for opal, and it's wonderful to have that opportunity again to talk about something that I love and my family's been involved with now for over 50 years. So let's just see how we're going here with I presume it's going to work. Okay. There we go. So opal has a very long history, in fact. It was first discovered in 4000 AD in a cave, obviously habitated by cavemen, but there was opal in there that didn't come there geologically. They were brought there. So this was in Kenya, and it was discovered by a Dr. Lois Leakey in 1939. So this was the first evidence of opal being used as an adornment, and it actually confounded all the theories because the first opals were originally thought to have come from, Hungary. Of course, that was impossible because here was opal in Kenya. And this was before the discovery of the current Ethiopian opal mines, of course. So a lot of the early opal was obviously Ethiopian. So opal derived its name from the Italians. It comes from the word opalis, which means changing colours, I believe. Correct me if I'm wrong, there's Italians in the room. But it was loved and adored by the Romans 2,000 years ago. In fact, Mark Antony tried to buy an opal from Senator Nonius for his wife Cleopatra, and Senator Nonius refused to sell the stone to Mark Antony, and as a result he was expelled from the realm, the Roman realm. So it was highly valued then, and it's highly valued now. This is actually a 1600 print of the works of Pliny, the first writer of natural history. So Pliny the Elder wrote the natural history of the world in 77 AD, and he stated that opal was the most valuable of all gems, and I'd have to agree with him on that. Shakespeare wrote about opal and referred to them as the queen of gems. Napoleon gave Josephine a beautiful opal the burning of Troy. And Queen Victoria, where are we? Where's Queen Victoria? There she is. She was a lover of opal and presented opal as gifts to most of the royal family around the world. The two pioneers here in opal were Tiffany and Cartier, the first major fashion houses to use it at the end of the 19th century. This is Australian opal that I'm talking about. Opal was just starting to be discovered in Australia in the late 19th century, so late 1800s. What is opal? Well, it's hydrated silicon dioxide. We've got some students in the room somewhere. Where are you guys? Okay. I must have slept in this morning, all the students. They're coming for it tonight. So it's opal can take many forms, but it contains somewhere between 3 and 6% in its atomic structure, water. That's in the atomic structure. So that's not water that comes in or out of the stone, that's built into it. So that's why we see the NH2O. Precious opals are composed of minute spheres of silica, and when they're arranged in the manner on the left there, in an orderly fashion. So if you imagine if you had marbles in a glass vase and they were all exactly the same size and you shook them around, they would all settle nicely and you'd have an orderly array of the marbles, however you shook them. And that's what happens in precious opal, where you have a play of colour, you have this orderly array of spheres. When you have different size marbles in the glass jar and you shake them about, you will have a disorderly array and you'll have different spaces between the marbles. And that's where we have common opal. And common opal, it doesn't have a play of colour, so white light comes in and it comes back out as white light. So you'll have blue opal or pink opal or fire opal. You don't have the play of colour. So precious opal requires this very special set of circumstances where the spheres are the same size and orderly and in an orderly array. So the colours, obviously all the spectral colours can be found in an opal. So we still need that orderly array, but bigger spheres will diffract white light out as red, and the smaller spheres will diffract the white light as blue, and all of the colours of the spectrum. So opal is one of those stones, unlike many gemstones where the colour you're seeing is a mineral causing that colour. Opal is refraction of light, and that's why you get this phenomenal display and this incredible movement. So the founder of modern gemology was Richard Liddicoat, and he made this quote, and it's stood the test of time. He said that if we're evaluating evaluating a gemstone or trying to grade gemstones, a diamond would be the easiest to evaluate. That would be a 1 on a scale of 1 to 10. And at number 10 was opal, the most difficult. And that has been, I guess, true to this day, and it's a challenge, for my company and for my industry, the opal industry. It's a challenge because people find it very difficult to understand. So it's important that we all, when we're learning or educating or studying or looking at opal, that we know as much as we can about it. We're going to talk a little bit later about some of the things that are happening around the world to help people better understand opal. So I wanted to kind of give you some incredible facts about opal that don't happen in other gemstones. So this is not only a gem, but it has these incredible relationships with nature. And the first one is the fact that opal has been found on Mars. A meteorite struck the Earth in Kenya. No, not Kenya, near Egypt. And it was discovered by Professor Martin Lee that there was opal in the meteorite, fire opal, in this meteorite. So big deal. Well, it is a big deal. The fact that there's opal in a Martian meteorite means there was water on Mars, because opal cannot have formed without opal. So they did some further work and discovered that, in fact, yes, there is opal on Mars today. So the next question, if opal has been found from Mars on Earth with water in it, could it have been containing microbes? Could it have brought microbes to Earth? Obviously, to form life, you need microbes. So was Martian opal an ingredient for life as we know it today? It's a question that is being looked at. So here we have an incredible relationship with opal and Mars and maybe the foundation of life on Earth. This is just some of these slides are from our collection, and this is an anhydrite with water. You can see the water bubble in there, which moves around like a spirit level. So we have precious opal, we have water, and we have air. So the water and the air is at least 35 million years old, more likely to be more than 60 million years old. So we have a few of these anhydrites. There's another one there we call a duck, but a little eye moves around. And we have a lot of interest from paleontologists wanting to take these things away, drill a hole, take the water and the air out and do scientific studies on it, which would be lovely, but we've resisted that temptation and we've kept them in our collection. This is something else that's quite incredible, and that's the fact that they've discovered that in Australian opal there is a prevalence of uranium in opal. And the incredible fact is that the uranium is it's in an inert form. So the question is, well, opal can hold uranium in an inert fashion. So is this the solution for storing uranium? Does opal hold the answer as to how we can store uranium safely? So opal may well play a part down the track with all of our advancements with nuclear science and nuclear energy. This is, some of you may know what this is. It's called an opal pineapple, but it's actually a pseudomorph. Opal doesn't form, it's in crystals. It's an amorphous gemstone. But here you can quite clearly see there's a crystal formation. So what happened when there was a mineral on the Earth called Ikeite, A-I-T-E, Ica-ite. It doesn't exist on the planet today. It disappeared at the end of the Ice Age, 65 million years ago. But the imprint of the Ica-ite, the formation, was left in the earth. And through a sedimentary process, opal came through. Glendonite was the first mineral that came and pseudomorphed it. The glendonite disappeared and the opal came about 35 million years ago and took on the formation of the Ica-ite. So here we have this one tiny little location, which we'll talk about later, White Cliffs in New South Wales, Australia. A tiny pinprick on the planet is the only place on the planet where you will find opal pineapples. They're extremely rare, and it's the only way you'll ever know what Ica-ite looked like. We have opalized wood. So this is some opalized wood from Queensland. This is some opalized wood from White Cliffs. And you'll see that line across the top of this specimen. Now, this is a great big specimen, so it's like a log. And that they are borer holes, so you can see that where the borers have been chewing through this ancient wood that became opalized somewhere between 30 to 60 million years ago. This is another specimen of borer activities in wood opal from Brazil. Quite incredible, and it's a network of holes. This is probably the most important opalized fossil in the world. So we have this relationship, opal and the dinosaurs. So this is a 2.7 metre long pliosaur. That was a marine reptile that existed 110 million years ago. It ruled the seas. It had 4 flippers, a very long neck, long teeth, and it was the primary predator in the sea. This specimen is in the Cody Opal Collection, in the National Opal Collection in Sydney, and it's about 70% complete, opalized. The whole fossil is opalized. It's very rare that you have pliosaur, complete pliosaur fossils, let alone opalized, precious opal fossils. That's a rib bone from a pliosaur. You can see the beautiful opal. That's a pliosaur tooth. And in the stomach area of the pliosaur, we've got the opalized remains of its last meal. So we have fish fragments. They used to eat stones as buoyant, to avoid issues with buoyancy. So there's quite evidence of exactly what they'd been eating. Shellfish and some of the tiny fish bones. Here's some opalized shells. We have gastropods and mussels and cockles and quite a few different types of shells that we found. These are from the ancient seabed that existed where all the deserts are in Australia. Was an ancient sea called the Eromanga Sea. And that dried up 60 million years ago. This is a fossil of an ancient squid. So you've probably seen belemnites in Morocco. So this is an opalized version of that. So this is the back carapace of like a calamar squid. This is another interesting one. This is a fossil belemnite. And then if you look at the close-up, you can see teeth marks from a big fish, ray that would have been eating it. So they're clearly the fish teeth marks, or the ray teeth marks of what ate it. These are opalized crinoid fossils. And on very rare occasions, we find shark's teeth. So these are opalized shark's teeth. So our collection is not fossils, it's opalized fossils. This is an interesting one. You can see in the top right there a small dinosaur called a hypsodontolontid. And it's, this is the femur from this animal that existed 100 million years ago. And you can see a couple of lumps. There we go. Here and here. So they're pathological lumps that are attributed to either teeth or claws. So this poor little fella got attacked by a bigger dinosaur, and it has teeth embedded in its bone. It obviously survived because the bone has grown around these lumps. So just incredible, the kind of things that we discover with these opalized fossils. And this cute little thing is a toe bone from one of those little raptors, those little hypsodophalontids. So it would have had a little claw coming off the end. And here's one in black opal. So these guys would have been, you know, 0.5 metre to 1 metre high. Little raptors. So they were meat-eating, fast little guys running around like Rui. Where are you, Rui? He's gone to sleep. Oh, there he is.
I just woke up.
He just woke up. Here's a beautiful bone on your left there. This is a vertebra, and you can see the incredible gem colour there, and another toe bone from a larger dinosaur. And probably the most important fossil, opalized fossil we've ever found is not the biggest or maybe the brightest, but it's the most important because, and it was featured on Nature magazine front cover. And it's the jawbone from an animal called Calicidon. And it was a little, I don't know whether you know what a platypus is, but platypus is a tiny little otter-like animal in Australia. So it was like a prehistoric version of that. And it was one of the first mammals on the planet. We all come from mammals. And so this fossil is extremely important to science. In fact, we lost it for 10 years whilst the researchers, the paleontologists at the University of Sydney were working on it. And it holds many secrets to life on Earth. And the professor, Mike Archer, who was studying it, explained to us that mammal fossils, forget about being opalized, any fossil of mammals from this period, 110 million years ago, there are so few that if you collected all of the fossils of mammals, the first mammals, and put them into a box, you could fit them in a shoebox and you'd still have room for your shoes. That's how rare mammal fossils from this period are. There's another pineapple. Now, opal, I've been talking about some of the curious, crazy things about opal, but now we'll look at the different types of opal from around the world. We have all sorts of opal that comes from 7 or 8 different areas of the world. And it's quite confusing because there are many different types. They look differently, they have different structure. There's opal CT, there's opal A, there's some that form in seams, some form in nodules, some form in fossils, some are common opal, some are precious opal. And it's there's a huge variety. So it's very difficult for those wanting to understand opal to have all of that information. Here we have the opal sets that my company put together about 6 or 7 years ago. We put together 60 of them, and they were sold before we'd even finished them. So most of the major labs around the world and educational institutes have them. So there's 213 examples on 9 different sheets like this, depicting every aspect of opal in terms of its locality, its appearance, its type, and also its value. So where is opal found? So in America, we have it in a number of areas, Nevada, Louisiana. So here we have some from Nevada. You can see there's a good deal of cracking. That's typical of a lot of the opal found in America. It's not terribly stable, so we don't really have commercial deposits, unfortunately. There's another example from Nevada. Idaho is another locality. And Louisiana, this is the kind of matrix with opal in it. So as I said, it's not terribly commercial. There's some beautiful Oregon opal from Opal Butte. Arizona even has some opal. It has some opaque opal and some blue opal. You're all probably aware of Mexican opal. It comes in a few different varieties. We have fire opal, which comes from yellow, orange through to red, generally in transparent type, and it's common opal, so there's no play of colour. We also, you can see some play of colour coming through in some of the fire opal, and we can have beautiful crystal opal displaying lots of beautiful colour. We also have the matrix version of opal called Cantera. So the opal's found in Magdalena, Correro and Zimapan. And there's some leopard opal found in Zimapan. Honduras produces a little bit of opal as well. It's quite unique. It comes from Erendique and San Andres. It produces some nice precious opal in basalt as the host rock. It also has some black opal. Brazil, we have opal coming from Piauí and Pedro Segundo, both precious opal and common opal. There's some beautiful examples of Brazilian common opal, not terribly common, but it's called common opal because it doesn't display a play of colour, but it's not common. There's some beautiful precious opal. I also have a cat's eye opal, which is quite rare. So the Slovakian opal is where some of the early opal used in Roman times came from. It was called Hungarian opal, but the area is actually Dubnik, which was originally Slovakia. So it was originally recognised in 1597, and it was sold in places like Constantinople, and Pliny, the older, who wrote the history of natural history, the book of natural history, he said they were from India, but clearly they were not from India because there is no opal in India. But obviously the traders were probably from India, and they said it was Indian, but it would have been Slovakian opal. We also have a new discovery of opal, well, new to the modern gemological world, in Ethiopia. So coming from Wello, Wegeltenner and Mezezel. So the opal from Ethiopia comes in different forms. This is the Mezezo opal. It's typical in kind of like thunder eggs with brownish orange opal with some play of colour. Often in these eggs you can see a good deal of cracking, quite unstable. The Wello opal was a later discovery and quite beautiful. It's probably the Ethiopian opal you see today on the marketplace. Beautiful colour, beautiful patterns. It's actually found in a river area, so these very steep cliffs, 1,000 metres high. So the area they're mining is, you can see I've highlighted there, is some 500 metres below the river level above the river below. And it's obviously got about 500 metres of overburden above. So it's very crudely mined without props, so it's very unsafe for the miners going up there, very unsafe working in the mines because there's a lot of collapse. And unfortunately, it's, the number of deaths and injuries are not reported very well. So I don't think it's terribly sustainable, this form of mining. But there's a lot of it, and it came onto the market 15 years ago in huge numbers. It was about 14 tonnes of rough a year exported to India. Today the number's more like about 4 million tonnes. And when you work it all out, after it's cut, it's some 2 million carats a year that comes onto the market. So there's very much an oversupply. And it's obviously the price of it's come down dramatically. And for quite a number of years, it affected the price of Australian opal because it was 1/10 the cost. It's now probably 1/100th the cost of Australian opal, but it's still being widely used. It's very beautiful, but it does need to be used with care because it's mostly hydrophane. We'll talk about that in a minute. There's opal discovered recently in Indonesia. It's certainly not commercial. It's volcanic version. It's mostly treated with cooking oil to darken it up to try and get colour from it. There's some more examples of Indonesian opal. And then, of course, Australian opal, which is found in these orange areas. The red dots are where opal has been found, and the orange area is what used to be the Eromanga Sea. So it's a dried up seabed, mostly sandy desert. And the formation of it is still not very well understood. In fact, as we speak, there are 3 models for how the genesis of opal happened. One is the deep weathering model, which is probably the most widely accepted one, and that's where silica-rich sands were washed through the earth, down through cracks with water, picking up chemicals along the way, and through some magic of some of the other minerals and chemicals in the earth, it somehow formed a gel, and the silica spheres enabled precious opal to form. And it's not really understood as to how quickly it formed, but we think maybe over 5-10 million years, and it happened 30 to 60 million years ago. So that's the deep weathering model. That just involved water percolating through the clay soils. The second model is the synctectonic model, and that is a model that it revolves around high pressure, hydraulic pressure from earth movement, pushing water through the earth, and also high temperatures of 100 degrees Celsius. And that still holds true. However, a Dr. Baer came along in around 2000, and he discovered the presence of microbes in Australian opal. What does that mean? Well, it means that we couldn't have had high pressure and high temperature, 100 degrees, because microbes don't exist in those environments. So it kind of dispels that theory in some ways, but today we're still not exactly sure. And we're not sure why there isn't evidence of microbes in opal in other deposits. So the first location I'm going to look at with you is White Cliffs. So you can see where it's located there. And this was the first discovery of opal. And the early miners there, they discovered surface material, and they came there on horseback and camel, had very crude operations, and this was some of the first opal that appeared in Europe. Some example of typical White Cliffs opal. The next area is probably the most productive area that the world has ever seen. That's Coober Pedy. And Coober Pedy is very flat, ancient seabed, and it's just anthills, so red earth, white mounds from the Mullock Heaps as far as the eye can see. And there were some 30,000 people descended on Coober Pedy when it was first discovered around 1920. Today, it's lucky to be around 2,000 to 3,000. So this is an aerial of Coober Pedy. These are some old workings close to town where people have buildings. Most people in Coober Pedy live underground because the temperatures there in summer are average 35 to 45 degrees. Often it gets high 40s. So the underground, the workings, the mines underground make beautiful, cool homes with a constant temperature year-round of 22 degrees. Some beautiful rough material there. The next area, not far from Coober Pedy, is Minturby. And Minturby is a much older deposit than Coober Pedy, so it's a little bit deeper, a little bit harder ground, and quite difficult to work, but it produced some incredible opal over a short period of time. Unfortunately for the opal industry and for the gem lovers around the world, the whole township that developed around the opal mining was closed down by the Australian government about 5 years ago to hand back to the Indigenous landowners, original landowners. and so the whole town now is a ghost town, and there's very little opal mining. There's a few miners that have managed to keep their operations going, but unfortunately we've lost that deposit. And this is some beautiful Minterby opal, distinguished by the matrix you can see on the outside, which is very hard. There's some more of it there. Andamuka is another area in South Australia near Coobapedy, a very old area, and you can see the crude way they lived. They had their house half underground, half outside. The town grew quite quickly when it was first discovered in about 1925, and unfortunately the deposits become more difficult, so there's not a lot of activity there now. In fact, most of the township work at a uranium mine nearby. So sadly, we don't see a lot of opal come from Andamuka these days. There's some nice Andamuka opal. And probably the most important or the most valuable opal comes from Lightning Ridge. So you can see Lightning Ridge is over towards the east coast. And it was the early miners there, once again, lived very crudely. The beautiful thing about Lightning Ridge is the history is very well preserved. So people, when a miner's worked out, they just leave everything and move to the next area. And now there is a historical overlay. So in fact, beautiful old camps like this, Fred Bodel's camp, is preserved. So you can just walk in and see it, but it doesn't get pulled down, doesn't get taken away. So this is how Fred lived. He's tiny little living quarters. And he was one of the early miners at Lightning Ridge. You don't own the land there, it's all government lease, so, and you're not allowed to build a permanent residence, but you can see there this stone, incredible stone place. So this was built by an Italian miner who went to Lightning Ridge. Locally they called him Amigo, and he didn't find any opal, but he found a lot of this brown hard rock. So whilst he wasn't finding opal, he was there for 30 years persisting. He was certain he was going to find his fortune. He didn't find any opal, but he did find this hard rock, and he built this incredible castle that's still there today. Now, this is typical of Lightning Ridge ingenuity. This place is not that old, maybe 30 years old, but building materials, there were no building materials. You couldn't build anything permanent anyway. So you use whatever materials you had. So the beer bottles are the windows. Then those windows were okay, except no ventilation. So you can see the car door, you wind the window down, and you've got a window that opens and closes in your house. So quite incredible. And nearby, this is an old DeSoto truck. So there would, obviously, you needed to have a toilet. You build it a little way away from the house. And so he used a prospecting shaft, which was 9 inches in diameter, or 300 mil. And he put the old truck over the top of it, cut the driver's seat hole, put a toilet seat there, and you could sit behind the wheel and go to the toilet. So that's still there from 40 years ago. And some beautiful black opal rough. Black opal distinguished by the dark body tone. So Lightning Ridge produces both dark, black and light opal. Here's some examples of black opal. So they're not black, but they're in a body tone that we call black. And we'll explain the body tone in a minute. So these are all just nothing done to these stones except cutting and polishing. No treatment. most incredible of colours coming from Lightning Ridge black opals. And Lightning Ridge opals can fetch today up to between 20 and 30,000 per carat. So right up there with very valuable diamonds. Red is the rarest colour in opal because, as I spoke to you before about the size of the spheres determining the colours that come back, red is the one that comes back to us the least because it requires the biggest arrangement of big spheres. Another beautiful fine black opal. This is a lighter body tone, beautiful crystal opal. Here we have blue-green, which is very popular, especially in Paris and with some of the big fashion houses. This is a beautiful pattern, one of the very important stones we've sold. It's harlequin-like. You've probably heard of the harlequin pattern. So very defined squares and diamonds would be harlequin. This is not quite harlequin, but a beautiful pattern. So Lightning Ridge at its peak was about 10,000 people. Today, we don't know, so that's the official sign when you come into the town. They normally have the population, but for Lightning Ridge, they have a question mark. But we believe it's about 2,000 people. So this is where I spend most of my time buying opal. And the Australian industry, in its peak in the 80s, it was estimated about 500 million, the value of the industry. Today, we estimate about $200 million worth of export. Now we're moving to the Queensland fields. So this is further north, and the opal from Queensland is distinguished by the host rock in which it's found. Generally found in open cut mining. The older miners would have used shaft mining, but today it's mostly open cut and heavy machinery. It's very remote areas that it's being mined, so it's difficult to move all your machinery to these locations, invest all your time and money, and then not find any opal. So it's these guys are risking everything to find a fortune. Some do, but many don't. Okay, so this is what they're looking for in the Boulder opal country. You can see the brown host rock, which is an iron stone. We call it iron stone. It's a very heavy sandstone, quite a lot of iron content in it. And opal is often found, but you find the ironstone concretions. When you find that, then you've got to break them all. And when you break them, sometimes you find these veins of opal. And you can see that one there is a split, so it would have been together and a very thin vein split on both sides. And if you have a nice clean face, you can cut a beautiful boulder opal on that. On the back of that stone will be the host rock, the brown host rock, naturally formed together. This was the most valuable boulder opal we've ever found, called the Galaxy, and it now resides in the Houston Museum of Natural History. And I think I'm getting a cue that we've got to wind up. So we'll move it along. This is boulder matrix opal. It's distinguished by the veins of opal. That's an opal nut from Yower. So we've got a few issues in the opal industry at the moment around the terminology, how it's being described, the non-disclosure of treatments, and the non-disclosure of the care instructions required. So we're getting a fail on all of these things as an industry and causing consumer problems. This is black opal that was available at a trade show in Hong Kong, a very big gem dealer. That's the sign he had, black opal. When I inquired about it, it took quite a bit of convincing for them to tell me that it's not actually black opal, it's smoke-treated Ethiopian hydrophane opal. So it started out white, and it's black because they've made it black. And this is what consumers are seeing. All of that there is described as black opal. It's not black opal. It's dyed or smoke-treated. Once again, black opal. It's not black opal at all. And one guy said he was from Sydney, another guy said he was from Thailand, but interestingly, using the same tweezers. So poor old consumers. This is a test we did. We started out with a 23.6 Ethiopian opal, and you can see what happens. You can see the little bubbles appearing after 9 minutes. And by the time the 51 minutes are up, you can see bubbles appearing everywhere. And it was like champagne, bubbles coming off this stone. So before immersion, 23.64 carats. After 1 hour and 9 minutes, 26.57 carats. More than 12% increase in weight. So where are we at? And I'm getting there, Rui. We're not using uniform classification. The educational institutes are not singing from the same hymn book necessarily. We're getting pressured to provide full disclosure. Hydrophane is not being described at all. The term boulder opal is being used for all sorts of things. The body tone scale has not been put into practice, so people are calling black opal that's not black opal. And the whole terminology is not terribly well understood. So what do we need to do? We're working now with CIBJO. We're not far away from releasing the opal guide, and the opal guide will sort all of this out, and hydrophane will be a characteristic that you should be describing. So you just do an immersion test. If it's giving off bubbles and putting on weight, it's hydrophane. And all the definitions will be described, and we'll have classification. You'll be describing the characteristics, the types. The localities are all described in the guide, and we are probably about 3 months away from releasing it with CIBJO. So it's been a wonderful effort by a lot of opal experts around the world, and this is the kind of things you'll be describing as gemologists. And there'll be information about, you know, the different kinds of the way you can describe things. And there's the body tone scale. N1 to N4 is black opal, and you can see there how we've arrived at, with some examples there. Even Mexican and fire opal, common opal can be described in body tone terms. Okay, so Rui, I got there. Thank you.
Indeed. And now the microphone is working. We don't have time for questions, although Damien, I took a lot of notes, so I did, because it was such an interesting talk. And thank you very much indeed. Thank you very much. I mean, thank you very much. Let's give another round of applause for Damien. And what a wonderful presentation, and very educational. He mentioned the CIBJO Opal Guide, and we happen to have on the room now today, and now the president of CIBJO, Dr. Caetano Cavalieri, that I kindly asked to reach out to the floor with Dr. Ilaria Adamo for a welcome note. Thank you very much. Yes.
Thank you very much, Rui. I mean, please, when you are on stage, stand up instead of be seated.
That was Damien's joke.
Just to quote you, Damien. By the way, thank you very much. I apologize with Thomas that I went through before you, but just to say, it was, to me, important to be here with you and to say a few words with Ilaria here next to me for 3 different reasons. Number one, because what you all do with FEEG, with my good friend and my other, let's say, member of our big family, is essential. And I say essential because the importance of laboratories and gemology is the element through which we may together, from one side and the other side, bring to the consumer knowledge, understanding, and improve the confidence that the consumer has towards our industry. The second is the capacity to let the new generation and the new gemologists and the new jewelers to have more knowledge about what our business is all about. The third is the importance of, let's say, the education. In CIBJO, we are the one who set up the academy, chaired by Ken Scarrett, that you all know, translating the technical part of the Blue Books in something that is understandable by everyone, not only by the people that is now seated here and those colleagues of us that are expert in reading this language. So we did, thank to Ken and his team, accessible to everybody. And we add to this what has been announced and now is ongoing, quite ready to be working, the Academy for students in order to teach them the manufacturing of high-quality jewelry done by those that were the head of the factories that now are retired. And the people that is retired doesn't mean that has to be put in aside. So we took them back, we are taking them back and teach to the young generation. So I want to express my deep appreciation to the European Federation of Gemology, to Ilaria, to Rui, and I apologize that my English has not the same accent as Damien Cody, coming from, where are you coming from? Australia. Australia, I think, is an island somewhere in the south, okay. But by the way, thank you very much. Thank you very much for what you do, and please consider CIBJO and myself at your disposal anytime. Thomas, I'm sorry that I took a little bit of your time, but thank you again, and I wish you great success. Thank you very much.
Thank you. Thank you, Gaetano. Grazie a te. Dr. Cavalieri is saying, please stand up. So I'm doing an effort because actually I was 1.90 meters when we met. But then because I was not behaving, Gaetano was cutting my legs, right, Dr. Cavalieri? Well, now it's my pleasure to call on the stage the pre-announced already by Dr. Gaetano Cavalieri, Thomas Hainschwang. It's a very easy name to say, but to spell for our Latin languages, to spell Hainschwang, it's really hard. Dr. Hainschwang, he's founder of the GGTL laboratory in Liechtenstein and also in Antwerp. He holds a PhD, and by the way, his thesis was on type 1B diamonds, and he also has a DUG, Diplôme Universitaire en Gemologie, that means University Diploma in Gemology by the University of Nantes. He's going to talk to us on his very high-level science, terminology and knowledge on plastic deformation and colored diamonds. Please give a big warm welcome to Dr. Thomas Hainschwang. Oh, the microphone is not working? Do you want a hand microphone?
No, it's fine. Don't worry about it. Okay. Great. There you go. Okay. Well, good morning or almost good lunch. So I'm going to lead you into your lunch break with my talk about diamonds. You're probably going to need something to eat after it, because I will be, unfortunately, as usual, talking quite a bit about spectroscopy. I'll be talking about a project, an ongoing research project on the effects of plastic deformation in diamond and the relation of plastic deformation of the different colors it can be observed in. To start with, I will give you an introduction into diamond color in general. So I will only talk about our actual project a little later. First, let's just talk about colored diamond in general. So diamond, when diamond is defect-free, it is perfectly colorless. It has a large band gap, so the energy needed to make electrons move into a region where they absorb light is far too large to permit such transitions to occur. Diamond, on the other hand, can occur in virtually any color. This color depends on a range of defects in diamond, but not all of them are just impurities as we know them. So we have color-causing defects that can be impurities or structural defects. So these color, the color cause of brown diamonds has been defined a long time ago as being vacancy clusters. So that's an aggregate that consists of a large number of vacancies. And those are related to post-growth plastic deformation. So that's where the plastic deformation started to play a role. Before, let's say around the definition of this plastic deformation related defects was made in the late 90s, early 2000s. Before, we only knew, okay, they were plastically deformed, but what exactly was the defect was very unclear. At some point, it was believed that only the lattice, the deformed lattice by itself would cause the color. Later on, these so-called vacancy defects, vacancy clusters were defined. Now, understanding the color causes of diamond in general requires, requires absorption and luminescence spectroscopy. So that's why we will talk spectroscopy quite a bit in my presentation. Okay, little image. This is what diamond can come in as colors. So you've got anything from colorless to white. White being, everybody calls colorless diamonds white diamonds. That's not what they are. White diamond is this on the right side here, this down here. So diamond occurs in pretty much any color that you can imagine. Quick recap of the instruments and techniques used, just so for the ones not so familiar with it, you see what we're using. So as I said, it's absorption and fluorescence spectroscopy. Absorption spectroscopy, what light goes through your sample, what is being absorbed by the sample, and you will see on the screen at what wavelength it absorbs, at what wavelength it doesn't absorb, but it transmits. And we do this from the UV all the way to the mid-infrared. Usually we use, it's usually divided by by 2 to 3 instruments. One instrument is the UV-Vis NIR spectrometer that covers the UV all the way to, usually, well, it depends what instrument you have, but most of them cut off at around 1100 nanometers. And then you have the infrared spectrometers. Modern infrared spectrometers cover the range of 8,000 wave numbers being about 1200 nanometers or 1250 nanometers to 25,000 nanometers. Given in wave numbers, typical for infrared spectroscopy, but you can transform these directly into nanometers. And then we also use a near-infrared spectrometer specifically for near-infrared spectroscopy, as it permits us to do low-temperature spectra in the near-infrared, which is impossible with an infrared instrument. Fluorescence spectroscopy, well, fluorescence is directly related to absorption. So you have light being absorbed and electrons rising in their energetic state. When those electrons fall back to their ground state, a lot of this loss of energy is happening through fluorescence, not all of it. It can also be just lattice vibrations. Fluorescence, hence, is the emission of light by, in this case, diamond. We excite fluorescence by either ultraviolet light or by laser light. It can be laser in the UV range too, but I'm just talking about monochromatic versus non-monochromatic light. Here is a laser Raman photoluminescence spectroscopy system using 7 different excitations from 360 to 785 nanometers. Importance here is we have to use a range of lasers in order to detect as many defects as possible. This is a fluorescent spectrum. So basically it shows you at what wavelength your stone emits. This, since we're centered at about 520 nanometers, correlates to green fluorescence. This is the H3 center. Typical structure in diamond, you have a zero phonon line, which is a purely electronic transition. And then you have the vibronic bands that all relate to the same defect. So this entire band that you see here is the H3 center, oftentimes only noted the zero phonon line and not the other ones. Okay, quick look at the defects and color origins of diamond in general. Defects, as I just explained, always the same look. You have a zero phonon line, you have vibronic bands. Zero phonon line, vibronic bands. And here you see the correlation between absorption and luminescence. On the left, you have the absorption spectrum of this defect, and on the right, you have the luminescence spectrum of this defect. Absorption spectra and luminescence spectra, they have the same zero phonon line. So here, this is GR1. They both have the same zero phonon line, but in absorption, you will have the vibronic bands at higher energy, lower wavelength, and in luminescence, you have it at lower energy / higher wavelength. Oftentimes, these spectra are almost mirror to each other. Here, not quite for a range of reasons, but, you know. So diamond is very rich in defects. We have the so-called intrinsic defects, which are defects of just structural importance. So you have like carbon atoms missing in the lattice. That's what we call a structural defect. When we have actual impurities present, like nitrogen, boron, other defects, nitrogen-based defects, then we have impurities involved. This is the most common thing in diamond, that we have impurities, so yellow diamonds, etc. Let's look at the most common colors in diamond and the most common defects. So this is, This is the typical so-called Cape diamond. So the typical yellow diamond that you see in the market is very likely a Cape diamond. Cape being, from South Africa, from the Cape, because they were very well known for their yellow diamonds, lighter colored yellow diamonds. With modern cutting, a lot of the Cape diamonds that you see nowadays also represent vivid yellows, deep yellows. These can all be Cape diamonds, thanks to modern cutting. The Cape spectrum is this one here. So this is an absorption spectrum. The Cape line is this 415 nanometer band here. It causes yellow color and blue fluorescence. So that's a very, very common defect that we rely on very much on the identification of synthetic diamond, for example, because it never occurs in very strong intensities in synthetic diamond, at least not in colorless synthetic diamond. Now, this is a much rarer type of yellow diamond. So these are type 1b yellow diamonds. This is what we all know as canary yellow diamonds. They're colored by single nitrogen instead of aggregated nitrogen as the N3 center. Now here it's the C center that colors these diamonds. You can see the spectrum is very different. It's just a continuum. no absorbance going on anywhere until about 560 nanometers. At 560 nanometers, your spectrum shoots off, and that's what causes this very intense and bright yellow color. Orange to pink-orange diamonds of the 480 nanometer type. These stones are in the market. What you find today, those represent the most expensive diamonds of all of them. So those are those vivid oranges. When you get like a pure orange or a pure yellow orange of high intensity, and with this strange orange reddish fluorescence to it, that's this material. This material is characterized by this strong band here, which is likely related to an oxygen defect, but it's not definitive, but that's just a preliminary result that were drawn from various publications on this defect. And what's particular on them is that while under a UV lamp, they fluoresce yellow. So, you'll always have like yellow fluorescence. They actually fluoresce red to visible light. And this is what you see here. So these wiggles here is actually the fluorescence to visible wavelength. If you excite this diamond with a green laser or with a blue laser, it will fluoresce red. And this red fluorescence adds to the intensity of the color, hence a positive effect of fluorescence for this diamond. Blue diamonds colored by boron, pretty boring spectrum, so it's just a continuum, and this is the kind of colors you can see. This kind of boring and kind of not very steep spectrum is the reason why blue diamonds are never very, very, very intense in color. So even if you see vivid blue, it will never be a sapphire blue, because this kind of spectroscopy just doesn't permit it. It's not possible. Green diamonds, here is a historical from the Natural History Museum in Vienna, colored by natural irradiation. You can introduce the same thing by artificial irradiation easily. These stones are supposedly all naturally colored. A very difficult topic. Then we get into the topic of the day, brown to olive type 1A diamonds. These are colored by the so-called vacancy clusters, brown and olive. So olive being just a mix between brown, green, yellow, okay? All these colors are related to a continuum absorption. That's the main reason of the color, plus some minor things like N3, the 560 band that we know from pink diamonds, etc. And here we get to the pinks. So pink to red. Pink to reds are also colored by a continuum, but overlaying the continuum is a much stronger band at around 550 to 560 nanometers. Plus, many of them also have this unusual doublet here at 390 nanometers. Pink to red is exactly the same. So if somebody tells you red is much rarer than pink, that's just a darker pink. And if you have seen reds in the market, well, some of the deep pinks you'll see are actually prettier than the reds. And some of the reds we see, I'm like, okay, we wouldn't grade this as red. But, it's always a question of definition. So these are all red diamonds. These are purplish pink, more of a vivid pink. Pinks and browns can be of any type except type 1, except the pinks can't be type 1b naturally, but they can be type 1, and they can be type 2, which is the reason that it has been hypothesized that nitrogen plays no role in it. So this is the topic we were working on. Actually, we limited ourselves to type 1 diamonds. We didn't work on type 2s because it's not really important and they're harder to find. And also, what we're looking at is this color by graining. The graining in type 2 diamonds is much less defined than in type 1s. So we're looking at type 1 diamonds that are colored by this graining. This is the kind of colors you see: browns, olives, olive, and pink to red, and purple as well. So these are the colors we're talking about. These are all colored by this. So you see these funny colored lamellae traversing the stone, in brown, in olive, and in pink. And these lamellae always correspond to strong strain when you check the extinction and strain when you check the stones on the cross-polarizing filters, as shown here. So these lamellae are directly related to deformation, plastic deformation, slip along the octahedral direction. This is all strain and anisotropy from post-growth plastic deformation. There you go. So what's similar about them? Similar about them is, first of all, we got the colored lamellae in all of them. The most important part is that these colored lamellae can have the same, can have various, up to 3 colors in the same sample. So you can have one diamond that contains pink lamellae, brown lamellae, and olive lamellae, which clearly shows they're pretty much the same. But the question is, what's the difference? Why does it occur? Why does it happen? Excuse me. Fluorescence. Here you can see the same thing. So these are basically the color lamellae that you see in those samples. And the fluorescence, as it is concentrated here, is from the H3 center, which is a vacancy, nitrogen vacancy defect. So you can see that within those colored lamellae, you have very elevated quantities, concentrations of nitrogen vacancy defects. So that's something you see in pink, brown, and olive diamonds, identically in all of them, this green fluorescence. You may not see the green fluorescence in a pink just by using a UV lamp, because the N3 center is extremely dominant. So in a pink diamond, you will see blue fluorescence. But on the other hand, if you use a laser in the blue wavelength, you will not excite the N3 center, and then you will see this green fluorescence popping up. So it's very, very common for deformed stones. Now, the differences between them is mostly found in the absorption spectroscopy and in the fluorescence spectroscopy. Like the most important part is the infrared. In the infrared, brown to pink diamonds, brown to olive diamonds all have a strong amber center. I'll show you in a minute what that is. They also occur as 1A, 2A, and also 1B diamond, while pinks, purples, reds do not exist as type 1B. They only exist as type 1A and type 2A, which makes total sense. When you will see the conclusion of my talk, you'll understand why this is. The amber center thing I just explained. Browns and olives have typically a higher nitrogen content than pink, purple, and red. And also most of the pinks have far higher nitrogen aggregation than brown diamonds, but this is not always the case. Here, okay, let's have a look at some infrared spectra. So we have brown versus pink diamond infrared spectroscopy. You can clearly tell the two are not the same. So in brown diamonds, we have this region here, that is the near infrared domain. In the near infrared domain, in brown diamonds, you have, in all cases that in stones that contain nitrogen, you will have an amber, so-called amber center absorption, okay? This absorption can be very strong and it can be very weak. It's very weak in stones that are mainly type 1A, B. So the less A aggregates, the weaker the amber center. And the amber center correlates, actually, as long as your stone is mainly type 1AA, the amber center intensity correlates directly with the darkness of your stone. The darker your stone, the stronger the amber center. Pink diamonds, when they're really pink, there is no amber center. You see orangey pink, you will have amber centers. The amber centers are weak, but many of the orange, so-called orangey pinks from Argyle, for example, contain a really small amber center in here. And that correlates straight with some brown lamellae that are contained in the stone, because that's actually what gives you this orangey appearance. Here, the near-infrared domain of some brown diamonds taken at low temperature. So this has been taken with a special near-infrared spectrometer at liquid nitrogen temperature. And you can see that the amber center has a range of 0 phonon lines and all these vibronic bands that range all the way to about 1200 nanometers. This is typical. The one in 1B stones, the amber center is different than in 1A stones, but you can actually transform them via treatment, and that's part of our project here. Difference between them, well, you've seen it in the UV vis NIR spectroscopy. This distinct 560 nanometer band is only strong in pinks, while it is really weak in browns. Many browns exhibit a 560 nanometer band, but it's really not very distinct. And that's why you have these pinkish browns, you have pink browns. That's why we have all these intermediate colors. And then one important thing is in the photoluminescence spectroscopy, there is this band here, this funny and strange band that is almost omnipresent in brown diamond, and it's very, very uncommon in purple to red diamonds, and usually only present if you have brown lamellae in the stone. So here the UV-Vis comparison. Brown is mostly continuum colored. Pink is a continuum as well, but this strong 560 nanometer band that causes the color. This is actually the color suite of Rio Tinto. So here you have the lightest Rio Tinto color to the darkest Rio Tinto color, not colored red yet, not called red yet. So that's their color references. Okay, so what did we do? We took stones that contain colored lamellae in all colors, and we treated them at different temperatures in our high temperature furnace. And then we went for HPHT treatment afterwards. But the first thing we did, we heated them up to 1500 degrees Celsius to see how they behaved and what happened in spectroscopy, what happened at which temperature. The question was, will we be able to modify in a stone that contains olive, pink, and brown lamellae, will we be able to modify one color while we don't modify the other ones in order to understand the formation of all this? Here are the first samples. In the meantime, we actually got more, just bought some 10 more samples, bigger ones, with such lamellae to do more experiments on them. These are, I mean, it's kind of hard to see, but this is pink plus brown. There is some pinkish in here. This is also contains some pink. This olive one here, if you look at it in immersion, it will have all colors. So it has pink, olive, and brown in it. Just a big mix of it just turns out to be olive. This is just pure pink to see what happens to them. And these are slightly pinkish browns. Hard to see on images, but as soon as you go into immersion, you will then see it. So here we go. Here we got one sample, two sample. This is the olive stone here. In here we have olive, brown, and pink graining. The pink graining is kind of hiding in here, so it's kind of hard to see because the pink graining is really associated very close to the browns, and it's spaced within the brown layers. Here you see the pink. Here you have clearly pink plus brown. And the samples we have, they have the typical spectroscopy, nothing too unusual here. Infrared spectroscopy, nothing too unusual either, exactly what we expected. The browns have an amber center, the olives as well, and the pinks do not. So pink down here, the amber center is practically absent, which is the typical and expected result. And also down here, the pinks very low in nitrogen. This stone is actually a type 2A, and the browns and olives are higher in nitrogen. Now here starts the interesting part. What happens upon annealing? So this stone was annealed at 1500 degrees Celsius and at 1800. And I had annealed it also at lower, so it was annealed at about 1000 first to see if something happened. We went steadily up to see at what temperature actually something dramatic happened. and it was around 1500. Some of the stones started to slightly change around 1150, but 1500 was quite dramatic. So before, we have this amber center with a peak at 4068 and 4165. This is a typical spectrum for an olive stone. And after the 1500-degree annealing, the peak at 468 disappeared, and 465 became the only peak present. And what happened to the stone? It shifted from olive to straight brown, or pinkish brown, actually. So this is what happened at 1500. Now, we went to 1800. What happens at 1800? At 1800, 4165 decreases by a factor of about 2.5, and the color gets lighter and much more pinkish, which is a really was a very surprising result. Here you see the whole thing at low temperature. So before and after, that's just 1500, the 1800 I had no time to do. And in luminescence, I said before, in browns, we have this strong center at 617. Well, before the treatment, the center is practically absent, and after 1500 degrees, we form a very strong center at 617, 626. After 1800 degrees, it just decreases a little bit in intensity. And this worked for all samples. So in all samples, we basically shifted the 4068 was gone after heat treatment at 1500 degrees Celsius. The ones that did not have a 4068, not much happened. Okay? So there is a clear-cut correlation between the 4068 and 4165, and also the formation of this strong luminescence band here. Now, this is a short intermezzo to show you a thing that just got cleared during this study, that for pink diamonds, in pink diamonds have a very strange photoluminescence spectrum. So this is a 532 nanometer spectrum. This is at 635 nanometer spectrum. These spectra are almost the same at room temperature as they are at low temperature. And I always wondered why this was. Why do we have these strange bands? So here you see the first order Raman peak. A Raman peak in a diamond is usually just a very sharp, narrow peak. In pink diamond, on the other hand, it's this weird asymmetric thing here. And that's the case for all type 1 pinks. Here at 635, you see even more dramatically. So working through this and doing experiments at room temperature and low temperature, I got to the conclusion that what we're looking at here is not photoluminescence, but what we're looking at here is Raman signal. So these bands here and these bands here are not photoluminescence, but they're Raman peaks. And looking through the literature, the thing that they correlate straight and quite directly to is graphitic carbon. So we're looking at very likely the influence of some amorphous carbon types being part of the defectiveness of these diamonds. Now here we still have to go on to understand it further, but it's clear that, especially since the importance of this spectrum down here, I didn't even get into it. Here we use the 635 nanometer laser, and that laser has a pretty poor quality. The Raman quality of a spectrum correlates directly to the laser quality. So if you have a good laser with a narrow laser line, the Raman bands will be narrow. If your laser is terrible, so it has a large band, your Raman bands will be wider. So what happened between 532 and 635, quite obviously, the bands all got much broader, which shows straight and proof that this is Raman signal and not photoluminescence signal, because photoluminescence signal is independent of the laser quality. It doesn't matter if your laser is good or not, your stone will fluoresce. Okay, so let's go a little further. Let's look at type 1b diamonds. and the same topic. Type 1b diamonds are supposed to be yellow, okay? So you have diamond, you have single nitrogen, it will turn out yellow, just straight yellow. And the more single nitrogen you have, the more intense is your color. And if you have too much of it, well, it will get a bit too dark. But they're not supposed to be this. And that's what they actually are. So type 1b diamonds are not just yellow, like the perfect example, but the very vast majority of type 1b diamonds that you will see in the market are actually in this color range here. Now, why is this the case? Why are they not just yellow? Well, looking at the spectroscopy of samples and doing some HPHT treatment experiments showed that it's exactly the same reason as what I showed before. So prior to heat treatment, you have this spectrum here, strong 4065. After heat treatment, the 4065 disappears, and you form 4115 instead. Okay, the spectroscopy changes from this to that. The stone changes from olive to brown. So the type 1bs did exactly the same as our type 1a samples. Looking at orange, it does the same. So you have an orange stone, brownish orange. Why is it brownish orange? Well, people said, well, more nitrogen, I don't know what. No, it's not. It's plastic deformation. So this stone, brownish, deep brownish orange, brownish yellowish orange color. Before HPHT treatment, you have this spectrum here. After HPHT treatment, the stone turned bright yellow, and this is the spectrum you have. What's the difference between the two? This continuum here. Okay, the difference of the continuum after treatment, your continuum starts around 560. Before the treatment, your continuum starts already at 950 nanometers. So, conclusions. Looking at all the data, we came to these most important conclusions here. We have, first of all, brown, olive, pink grading in one single diamond. It's a very similar color origin, obviously. We propose that the different colors are the cause of plastic deformation under different conditions, because that's the only way to explain it. We can't explain a different color origin. It's just the formation is at different conditions. So what's being proposed? That the three colors are caused by different configurations of vacancy clusters with or without other defects involved. That's not quite clear yet. We're suggesting that the olive color is created by plastic deformation at the lowest temperature. Brown color is caused by plastic deformation at an intermediate temperature, and pink color is caused by plastic deformation at the highest temperature. Explains why we don't have type 1b diamonds in pink, because their deformation happens at such high temperature that all the single nitrogen would be aggregated. So it's impossible to have type 1b in pink, at least naturally colored, it's impossible. So the presence of three different colors in one diamond is quite easily explained. You have three different individual deformation events occurring at different temperatures. So your stone forms, is being plastically deformed, moves, or the temperature locally changes, it's being plastically deformed again, and moves or temperature changes and is being plastically deformed again. And there you go. There you have three different colors in your sample. And with this, I finish my talk. Thank you so much.
Thank you. Thank you so much, Thomas. I think Thomas has shown you how critical it is to really understand the fundamentals of what is happening inside a diamond, so we can understand how it behaves under the laboratory. Another thing that he highlighted is we need to learn and to get knowledge about spectra. And not only interpreting the peaks of the spectra, but also understanding the excitation energies that we use to obtain those peaks and the calibration of the instruments so we can rely on the data. And that is a very, very important matter in scientific gemology. We do have some time for questions. Is there any question in the audience or anybody that wishes to address a question to Dr. Hainschwang? even difficult questions. If there isn't, I have one. I have one because you mentioned liquid nitrogen and the type of conditions how diamonds are studied. And you work a lot with museums. I occasionally also work with museums, but sometimes it's very hard to communicate with the museums, usually for art history museums, because they might not understand how gemology, how gem testing is done. How can we, as gemologists, talk with the directors of museums to make them more more knowledgeable about making a decision into accepting gem testing projects?
The problem is that you have relatively few curators of collections that know gemstones like a gemologist. For example, I was really in a lucky situation with the Natural History Museum in Vienna, that Vera Hammer was a gemologist as well and not just a mineralogist. But the combination of the two, obviously she understood. So she let me analyze all their jewelry in liquid nitrogen. I mean, I put rings with those green diamonds. The ring, we didn't unmount them. The rings were in liquid nitrogen. So basically, she trusted me 100% on that. And nothing ever happened, obviously, because, you know, she knows diamond. And we have other cases like other museums where there's just a curator or a responsible person who may be an art historian in many cases, but not a research scientist from the geological field or from gemological field, and they don't know. So we have the case of the Dresden, for example, but since we're working so much on green diamonds, I've inquired if we could test it. And
you mean the Dresden green,
the Dresden green diamond.
The Königsgewölbe in Germany.
Yeah, exactly, because the Dresden green diamond, just for information, is the only naturally colored green type 2A diamond known in existence. All others are just stones in the market. Okay, and if it's a stone in the market, we do not know 100% if the color is natural or not for greens. So as a reference sample, this type 2A diamond would be invaluable. George Bosser achieved to study it in the late 80s. They had a different curator, and he convinced them that they let him test it at liquid nitrogen, but he was limited to UV-vis spectroscopy and infrared spectroscopy. Now, we wanted to do a PL study, like doing everything on the sample. And the curator that's in now is scared of the liquid nitrogen. So he's afraid that his invaluable stone could possibly break. So I had several discussions with them, but it was so far without success. I mean, I explained to them, look, I cooled absolutely every gemstone that you can imagine, including emeralds, aquamarines, whatever you want, and I've never broken anything except the calcite. So trust me, with diamond having the highest thermal conductivity of any material on Earth, nothing will happen to it. But still, they were too afraid to cool their sample. So it's kind of difficult. I think it just takes a lot of convincing until maybe sometime they might agree on it, but it's hard.
Maybe an article on a peer-reviewed magazine on how safe can it be and the resistance of the materials from a materials perspective might help them understand the subjects.
Yeah, that might help. Indeed.
Thank you very much, Thomas. And don't leave the stage. We don't have any more time for questions. Sorry about that. We do have some time for lunch now as we go out on your right, and we will convene here 15 past 2. 15 past 2, no 15 academic minutes more. We will try to be sharp at 15 past 2. Thank you very much indeed. Thank you. Thank you, Thomas.